All right, so this is, we're going to be doing exponential growth and exponential decay, which are specific types of graphing equations that measure growth that accelerates, things that take off. So like exponential growth would be like, I think we mentioned the bunny example, how every bunny has like 15 bunnies, and then those 15 bunnies have bunnies, and those bunnies have bunnies, and soon you have thousands and thousands of bunnies. That would be exponential growth because the number gets larger at a faster rate. So Roman numeral 1 is, we're going to do the exponential growth formula. The exponential growth formula, and then we're going to do a graph. So the exponential growth formula is y equals a times 1 plus r to the power of t. All right, in this equation, the letter A is always the initial amount. It's how much that you start when time is 0. How much do you start with at 0? So A is your initial amount. The lowercase r is called the growth factor, which is the percentage of growth that's happening, 25%, what have you. When you do the growth factor, it has to be in a decimal form. So for example, if you have 6% growth, you have to use 0.06. If you have 32% growth, you have to use 0.32 in the formula. There are very few formulas where percentages are shown as a percent. They're almost always a decimal. Okay, so let's go on. What is y and t? So the letter y is the population at time t. So after t number of years passes, how much is there? You can also think of this as the new amount after time has passed. And then, of course, t is time. All right, so we're going to draw a sketch of this. All exponential growth formulas have an asymptote that is horizontal. So you offset your ruler a little bit and you draw it with dashes and it gets arrowheads. And with asymptotes, you put their equation on one end or the other. So this is y equals 0 and put a box around it. So asymptotes are guidelines. They're lines that influence how the graph looks, but they are invisible. So your graph is going to come close to that line, but it doesn't cross the asymptote. It just gets infinitely closer to it as it progresses. Okay, so on this graph, your x-axis is your time, which is t, and your y-axis is your population, which is y. So when t equals 0, a is the initial factor, so wherever a is, it's where you start. So that's 0, comma a. That's your initial factor at t equals 0. And then the whole curve is kind of flat looking, and then it gets steeper, steeper, steeper without ever really straightening out. It just gets flatter on the left and steeper on the right. And it goes upward because that is a growth equation. Okay, let's do an example using a population growth. Y equals 2 times 1.5 to the power of t. Okay, if you're looking for the growth factor, you have to realize that the decimal you're seeing on the inside is 1 plus r. It's 1 plus the growth factor. So it's really 1 plus 0.5. The actual growth factor is the 0.5, which is 50% growth. So you do have to separate the 1 from the decimal. If you're looking for the initial amount, it's the A value at the front of the parentheses, which in this case is a 2. Another question you're going to get on your worksheet is to find the y-intercept. This is kind of a tricky question just because it has a y-intercept. Your y-intercept is the same as the initial amount. So if you need to find the y-intercept, you just set t equal to 0 and simplify. Or you just look and see what the a is, which would be 2 for that equation. All right, Roman numeral 2, graphing. All right, we are going to graph y equals 2 times 3 to the power of x. So we're going to make an extended H chart. Okay, so first thing you always want to start with is if x is 0. If x is 0, we have 2 times 3 to the 0. And of course, anything to the 0 power is 1. So this is 2 times 1, which is 2. It's also the a value at the front. So let's put that on the graph. 0, 2. And then you usually want 2 points to the right and 1 to the left. So keep your points really small, like 1 and 2, and then maybe a -1. So if we do x equals 1, then we have 2 times 3 to the 1. Do the exponent first. 3 to the 1 is 3, and 2 times 3 is 6. All right, let's put that on our graph. 1, 1, 2, 3, 4, 5, 6. Now, as you can see, we're shooting way off the graph. So if we do 2, it's probably going to be pretty large. Let's calculate it and see what it is. So 2 times 3 squared. Always do the exponent first. 3 times 3 is 9, and then multiply last. So 9 times 2 is 18. So that one's way up there, so we're not going to graph that one. Generally, if it's above 10 or 12, we don't usually graph it by hand. Let's do the negative one, though. So 2 times 3 to the -1. Negative exponent means the 3 flip-flops to the bottom, and I have 2 over 3 to the +1, which is 2/3. You will get fractional points, and that is not only normal, it's a good indicator. So -1 up 2/3 is about there. I'm going to label it -1, 2/3. All right, now we're going to draw our asymptote. So use your ruler, draw a horizontal line that's dashed, give it arrowheads, and label it y equals 0. Then you're ready to put your graph down because it gets infinitely close to the line. It curves up until it gets really, really steep. And I usually put arrowheads that I color in just because it makes it easier to see where my line starts and stops. All right, flip your page over. Roman numeral 3. Transformation graphing. Transformation graphing. Sometimes the math is so complicated that instead of graphing the original, we graph the base and then we move the points around to put them where they belong. This also helps you figure out where the asymptote has moved to, so it has a pretty practical reason. So for transformation graphing, you graph the base, and then you move the points to the new location. Graph the base, move the points to a new location. Now, there's a couple things you got to memorize when it comes to transformations. So first thing we're going to start with is a horizontal translation. Okay, horizontal translation is done to the x. So let's say that our base graph is y equals 2 to the x. That's the one that we're going to start with. So if it's been horizontally translated, if y equals 2 to the x plus a number a, we say that that is a horizontal translation, negative a to the left. And you can abbreviate the heck out of that. Horizontal translation, negative a to the left. If it is y equals 2 to the x minus a, then it is a horizontal translation plus a to the right. So when it comes to horizontal translation, it's the opposite from what you're looking at. All right, so for example, we are going to graph y equals 2 to the x plus 3. So your base graph is y equals 2 to the x. It has the base, same base, but just a plain x. And you're going to get super good at running points for a base graph because we're going to use the same base graph on multiple ones. So once you get the points, you don't have to keep calculating the base graph. You just use the same points. So if x is 0, 2 to the power of 0 is 1. If x is 1, 2 to the power of 1 is 2. If x is negative 1, 2 to the power of negative 1 is 1/2. That's your base graph. So let's plot those on here. 0, 1, 1, 2, negative 1 up 1/2. And of course, you have an asymptote at y equals 0. And I'm not going to label these points because remember, this isn't your final graph. This is just your base graph. So your base graph comes up, looks something like that. Okay, so looking at our equation, it's an x plus 3, which means it is a horizontal translation minus 3 to the left. The sign is opposite. If it's negative, you go to the left. Now, if you move to the left, 3, what we're going to do is take our 3 points and just count 3 to the left. 1, 2, 3, 1, 2, 3, 1, 2, 3, and draw the new curve. This one is negative 2, 2. This one is negative 4 and 1/2. All right, so that's horizontal translation. All right, let's do vertical translation. Vertical translation. All right, we're going to use the same base graph. If you have y equals 2 to the x plus a number b that's not in the power, it's just plus b. That would be a vertical translation plus b up. Unlike horizontals where it's opposite, verticals are what you see is what you get. So if we have y equals 2 to the x minus some number b, that's going to be a vertical translation minus b down. Now, this is important. When you move the graph up or down, the asymptote moves with the graph. All right, so we're going to do an example. Y equals 2 to the x minus 4. Your base graph is y equals 2 to the x, and we already have these 3 points calculated, 0, 1, 1, 2, negative 1.5. So first thing you do is graph the base. 0, 1, 1, 2, negative 1 up a half. And with the base graph, the asymptote is right at y equals 0. So you've plotted the base graph, you've drawn the asymptote. Now we want to say what the transformation is. The transformation, because there's a minus 4 on the outside, is a vertical translation minus 4 down. That's what that minus 4 says. So take each of the 3 points in your base graph and count down 4. 1, 2, 3, 4. 1, 2, 3, 4. 4. And this is where your asymptote moves down 4. So count 4. 1, 2, 3, 4. And draw your new asymptote in. My new asymptote is at y equals negative 4. So label that. And the further you go to the right, the closer the new graph is to the base graph. So they get really close there at the top. And so this is the point 1, negative 2, and this is 0, negative 3. So we just counted downward. All right, flip the page. Okay, so the last one we're going to learn today, there are 2 more. Last one we're going to learn today, though, is reflections. Okay, so for a reflection, if y equals 2 to the power of negative x, so if the x has a negative on it, that is a reflection across the y-axis. If there is a negative in front of the whole equation, or a negative 1 times 2 to the x, either one of those, that is a reflection across the x-axis. So we're going to do y equals negative 2 to the x. Our base graph is the same, y equals 2 to the power of x. So I'm just going to copy those points we calculated, 0, 1, 1, 2, negative 1, and 1/2. So just like before, you're going to plot the base graph. So plot those 3 points, 0, 1, 1, 2, negative 1/2. And put your asymptote in there. All right, so we plot the base graph. And then because the negative is in front and not up with the x, we are going to reflect across the x-axis. This is your x-axis. So we're going to take the whole figure and flip it over. So if it's a distance of 1 up, it's now 1 down. 2 up is 2 down, half up is half down. And when you draw it, it should be a mirror reflection of the original. This is 0, -1. This is 1, -2. All right, so that's the basic information that we're going to do a practice problem. Some of these things come in combination with each other, so it's more than one transformation. So we're going to do y equals 2 to the x minus 1 plus 6. Now, just looking at this, it's x minus a 1. If you add or subtract a number to the x, it's a horizontal translation. So we have a horizontal translation. And remember, horizontal is always opposite. So plus 1 to the right. And then if there's a number added or subtracted to the outside, that's a vertical translation. So vertical translation plus 6 up. And with verticals, what you see is what you get. Horizontals are the only ones that are backwards. All right, so our base graph is y equals 2 to the x. And I'm just going to copy those same points that we did. 0, 1, 1, 2, -1.5. Okay, so go ahead and plot your base graph. 0, 1, 1, 2, -1.5. All right, so while we got the base graph drawn, we're going to go 1 to the right and 6 up. So take a point, go 1 to the right and up 6. 1, 2, 3, 4, 5, 6. Then take the next one, 1 to the right, up 6. 1, 2, 3, 4, 5, 6. And then the last one, 1 to the right, up 6. 1, 2, 6. And because we moved up 6, our asymptote moved up 6 with us. So our new asymptote is here, and it's y equals 6. And then we draw our curve. Now, retrospectively, you do need to figure out where the new points are. Got to have at least 2 of them. That's 2, 8. This is what? 1, 7. And then this one's 1, 2, 3, 4, 5, 6 and a half, just 13 halves. All right. Are there any questions?